This is my geometry course. Today we're going to prepare for test number 4. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. I've said it before, I'll say it again. You cannot pass a math exam without doing at least 2 days of studying. But it doesn't matter how many times you tell students to study, they're not going to do it. So in order to force students to do at least a little bit of studying, we're going to do a practice exam right now together, and I'm going to give you a practice exam for homework just like the previous parts of the course. And these exams are going to do two things. Number one, like I said, they're going to help you study for the test, but number two, they're also going to familiarize yourself with the test so you can't say that you were caught off guard. Now, these practice tests are not going to guarantee that you get an A or a B. In order to do that, you have to actually go back and make sure that you know every single thing that we learned and every single problem. But hopefully these practice tests will at least ensure that you pass the test in the next class. Now remember, the most important resource when it comes to studying for the test is the screenshots in the description section. Go to the description section, click on the time code where it says screenshots of the classwork, and you have everything we did in the last however many classes it's been. That's going to be your primary source for studying for the test. And as usual, I want you to attempt these problems before you watch me do them. If you can't remember how to do the problem, that's okay. But go ahead and attempt the problem first. Get your mind focused on what we're doing here so you can get the most out of these practice tests. So go ahead and try problem number 1, and when you come back we'll do it together. Alright, we're back. For problem number 1, we're going to have to use the polygon interior angles theorem, which says that the sum of the interior angles is equal to 180 multiplied by the number of sides minus 2. And so on the left side of the equation, we can go ahead and just add up all those angles. 130 plus 100 plus 98 plus 100 plus x is equal to 180 times the number of sides. Now let's count the number of sides. 1, 2, 3, 4, 5. So there's 5 sides. So n in this case is going to be 5. N is 5. Let me plug that in. So if you simplify, we get 180 times 3 and add all those up. 130 plus 100 is 230 plus 98. That's 328 plus 100 is 428. And you can use a calculator on that. Be aware that a calculator is allowed on this test. 3 times 180, that's going to be 540. And I want you to show this work. You may be able to do this in your head, but I want you to show the work. Now we're going to subtract 428. So 540 minus 428 is equal to 112. And be sure to write your degree symbol because that is an angle. So we found x is equal to 112. So if you got that one right, good job. If you forgot how to do that, that's okay. We're just warming up your brain here to prepare for the test. On to number 2. See if you can try number 2. And when you come back, we'll do it together. Alright, we're back. For this problem, we're going to have to use the geometric mean theorem for altitudes because we have an altitude here. Remember, there's the geometric mean theorem for altitudes, and there's a geometric mean theorem for legs. Whenever you have this number given, the altitude of the right triangle, you're going to use obviously the altitude one. So what that theorem tells us is that the altitude h is equal to the square root of these segments that are created when the altitude intersects the opposite side. So that would be square root 3 times x. But in this case, the altitude is actually 2. I believe that is the formula that we used. I don't really remember. It's good to write the formula down. And just to make things a little simpler, I'm going to change that x to a y. Actually, I'm going to change it to a b. I don't want to confuse things. So anyway, that's the formula. And we know h is 2, we know x is 3, and y is b. So now we just have to solve. So we're going to isolate b, but we can't do that unless we get rid of the we have to get rid of the square root. So we have to do the opposite of square rooting, which is squaring. You don't really need parentheses on the left side of the equation, but it just makes things look symmetric. So you get rid of the square roots, or the square root, and then you divide both sides by 3, and we see that b must be equal to 4/3. So if you got that one right, good job. Okay, on to number 3. Go ahead and try number 3. When you come back, we'll do it together. All right, we're back. We're going to have to use the same theorem we used for problem number 1, the polygon interior angles theorem, which says that the sum of the interior angles of a polygon is equal to 180 times the number of sides minus 2. And 18 gon means it's an 18-sided polygon. So all we have to do is just plug in 18 for n and calculate, and we're done. So it's a pretty easy problem. Now again, remember, you're allowed to use a calculator. So 180 times 16 in your calculator, that'll be 2,880. You can do that in your head if you want to, but most students would probably just prefer to do that in a calculator. So if you got that one right, excellent. So go ahead and try number 4, and when you come back, we'll do it together. All right, we're back. We're going to have to use the 45, 45, 90 degree triangle, and the reason for that is we're told that this is a right angle. Obviously that's 90 degrees. We're told that this is a 45 degree angle, but the triangle sum theorem, which we learned in a previous class, tells us that all the angles must add up to 180. So if you do the math, you find out that this angle down here must be 45 also. And that's why we have to use the 45, 45, 90 degree triangle theorem. Now, that theorem tells us that if you have a 45, 45, 90 triangle, like so, whatever this side is over here, I'm going to call it W, that side has to be the same as this side. And we know that from the isosceles triangle theorem. But this side over here is whatever these other sides are multiplied by root 2. And you must memorize this. I know what you're thinking. You're thinking, I don't want to memorize that. I don't need to memorize that. But you do. You need to keep this in your head for the next 5, 10 years, however long you're going to be in school, because this is extremely important in the math curriculum. And the 30, 60, 90 degree triangle theorem, which we're going to use for this problem, is also very important. There's 2 of these theorems that you need to know. You're going to see these special triangles thousands and thousands of times throughout your schooling. Okay, so that makes this problem very easy, because we can see that a side opposite a 45 degree angle, which we found out this side is 45, That's 2. So that means that W is 2. So that means that this side must be 2 also. So X is 2. Pretty easy. And Y has to be whatever this number is multiplied by root 2. So again, these W's over here, they're both 2 in our triangle. So that means Y must be 2 times root 2. So again, if you know your special triangles, that's a problem you can do very quickly. Now we go to number 5, a 30, 60, 90 degree triangle. So go ahead and attempt that problem, and when you come back, we'll do it together. All right, we're back. So I'm going to draw this triangle down here. And our theorem says that if this side opposite the 30-degree angle is W, then the side opposite the 60-degree angle is W root 3, and the hypotenuse must be 2 times W. That's the 30, 60, 90-degree triangle theorem. So we see that the side opposite 60 is 5, and that's the information that is given. So what we do is we have to find W, because once we find W, then we can plug it into all these other sides and find A and B. That's what we're looking for, A and B. So what we do is we take those yellow problems or the yellow part of the problem, and we set 5 equal to W root 3. We're going to find W. Divide both sides by root 3, and we get 5 over root 3 is equal to W. And typically we don't allow roots in the denominator, so we're going to multiply both sides by root 3. And we get 5 root 3 over 3. Now, if you're not sure how we went from here to here, you can go to my beginning algebra course. We talk about roots quite a bit, how to rationalize the denominators. We don't really have time to go into that now. But basically what I did, real quickly, and this may not really explain, but it'll get you started with the explanation on how to do this. I just multiply both sides by root 3. And again, with the information you learn in beginning algebra, when you multiply a root by a root, that's the opposite of square rooting. You're squaring. You're multiplying it by itself. So it just gets rid of the root. So if you got that answer, good job. Let's go on to part A. Now we know W is 5 root 3 over 3. I guess I shouldn't have erased that. So we know what W is. So we can say, well, first of all, let's say B is equal to whatever W is, which is 5 root 3 over 3. Because B is the opposite side of 30. So B is W, but we just found what W is down here. And this side, the hypotenuse, is just 2 times W. So we just take this expression here and multiply it by 2. So A is equal to 2 times W. So 2 times 5 root 3 over 3, which would be equal to 10 root 3 over 3. And you probably want to leave those triangles just so you can see your work there. Now this was not part of the answer. I should erase that rectangle. This was actually the answer up here. Sorry about that. I didn't mean to confuse. So A is equal to 10 root 3 over 3. All right, on to number 6. For the triangle below, find tangent B. So go ahead and try number 6, and when you come back, we'll do it together. All right, we're back. So tangent B, that's equal to, you want to look at your trigonometric ratios. Remember, you have to remember those trigonometric ratios. So we have to look at B over here, and we have to find the side opposite and the side adjacent and divide them. So opposite side of that angle is 8, and the adjacent side is 6. Now 10 is adjacent, but we don't call it the adjacent, we call it the hypotenuse. So tangent B is 8 over 6, but we can then reduce that to 4 over 3, and that is the answer. So if you got that one right, good job. Try part 2 of number 6, and when you come back, we'll do it together. All right, we're back. So cosine beta, so you look at beta, and cosine is the adjacent side over the hypotenuse. So adjacent over hypotenuse. Now, how come I know that's the hypotenuse? Well, it's the opposite, the 90-degree angle. So cosine beta is equal to 12 over 13. So if you got that one right, good job. Those are just memorization problems. They don't really require a lot of thought. Number 7, go ahead and try number 7. When you come back, we'll do it together. All right, we're back. So we have to look at the 48-degree angle, which is obviously here. And sine is the opposite side over the hypotenuse. So the opposite side of this angle is this orange side here. And the hypotenuse is R, because it's opposite the 90-degree angle. So opposite side over the hypotenuse. So if you got that one right, good job. All right, on to number 8. Go ahead and try part 1 of number 8, and when you come back, we'll do it together. All right, we're back. So if you're using an iPhone, you want to put, make sure you're in degrees. You should have a little RAD button at the bottom. If you push that button, it goes to radians. If you push it again, it goes back to degrees. So make sure you're in degrees. Enter 87 into the calculator, then push your sine button, and that's your answer. So sine 87 degrees, and it says to round to the nearest thousandth. So 0.998, and if we look at the number to the right of the thousandths place, that's higher than that's 5 or higher. So we just round 8 up to 9. And we want to write squiggly equal signs to show that that's actually an approximation. So if you got that one right, good job. Go ahead and try parts 2 and 3 and 4. And when you come back, we'll do it together. All right, we're back. So we don't need a calculator for these degree angles when you throw them into the sine, tangent, and cosine ratios, because we can just use the special triangles. We know the special triangles have these relations. We talked about the 45, 45, 90 degree triangle theorem and the 30, 60, 90 degree triangle theorem. So these triangles must have these side relations. So sine 45, you just pick one of these angles. It doesn't matter which one. You'll get the same answer for both. That's opposite. Opposite this angle would be x. So opposite over hypotenuse, which is x root 2. Now, if you have an x in the top and an x in the bottom, and they're factors of the numerator and the denominator, then that means they cancel out. So you just end up with 1 over root 2. But then you want to multiply both sides by root 2 to rationalize the denominator. And again, you can go back to my beginning algebra course if you want to review how to do that. And you get root 2 over 2. So if you got that answer, excellent. If you forgot how to do this stuff, that's okay. Again, this is just warming up your mind here to let you know what you're supposed to be able to do on the test. So tangent 45, again, if you pick any of these angles here, let's pick this one again up here. They're the same angle, so it doesn't really matter. Tangent is opposite over adjacent, so x over x. But the x's just cancel out, and you're left with 1. Any number divided by itself is 1, as long as the number is not 0. So, again, it doesn't matter how big or small the triangles are. If the side relations, they fit this description in these pictures, then when you divide, you're going to get the same ratio. So we don't need a calculator to figure out these certain angles. Now we go to the 30, 60, 90 triangle. Again, these are special triangles. Attempt part 4. When you come back, we'll do it together. All right, we're back. So we look at the 60-degree angle, and tangent is opposite over adjacent. So that's x root 3 over x. X root 3 over x. And again, when you have a fraction and the numerator and the denominator have a common factor, in this case x, they just cancel out, and you're left with root 3 over 1, which is just root 3, of course. And you don't have to rationalize root 3 because it's not in the denominator of a fraction. See, up here it was in the denominator of a fraction, but down here it's not, so you can just leave it like that. So if you got that answer, good job. On to number 9. It says, find the unknowns in the rhombus below. So we're told that this is a rhombus. And remember, a rhombus is a quadrilateral that has congruent sides. All the sides are the same length. This side, this side, this side, and this side. All 4 of them have the same length. So remember, a square is a rhombus, for example. But you also might have something that looks kind of like a diamond shape. So we're asked to find x. How do we find x? Well, we learned the rhombus perpendicular diagonals theorem that tells us if you draw these purple diagonals of the rhombus, then these purple diagonals are perpendicular. So that means that this angle here is a right angle. That's 90 degrees. But if that angle is 90 degrees, we know this angle up here, this purple angle up here, that must be 60 degrees. Maybe I should use a different color. 60 degrees up here. Because the triangle sum theorem, all the angles in the triangle have to add up to 180. So 30 plus 90 plus 60 is 180. A lot of different ways to calculate that blue angle, but it's got to be 60. So it's a 30, 60, 90 degree triangle. So what that means is let's pull that triangle out over here so we can see what's going on. We know that the hypotenuse is 4. We know that this is 30. We found out that this is 60. And we're trying to find x, and of course we'll have to find y also. Now I'm going to pull out that special triangle so you can get a feel for what's going on. Remember, if the side opposite 30 is w, then the hypotenuse is 2 times w, and the side opposite 60 is w times root 3. That's the relation. That's the 30, 60, 90 degree triangle theorem. So we have the hypotenuse. So that allows us to find W. Whatever the hypotenuse is, that's double the side opposite 30 degrees. So the side opposite 30 degrees must be half of 4. So y is 4 over 2, which is 2. So y is 2. Now, y is w. Well, now we're in business, because if we know what w is, we can find w root 3. That's x. So w root 3, w is 2, so that'd be 2 root 3, and we're done with those problems. Maybe I should just leave those triangles there so you can go back and remember what we did. So that was just another special triangle problem. So now we're looking for B. B is going to be very easy because this is a rhombus, which means all the sides are the same. So it has to be 4 because this side is 4. All the sides have to be 4. All these sides here, they all have to be 4. So that was easy. Now omega, we have to find omega. I call it W over here, but it's also a Greek letter. If you write it in a particular way, it's referred to as omega. In order to figure this out, I'm going to consider the rhombus right triangles theorem, which says that if you draw the diagonals of a rhombus, and in this case we see the diagonals, they're the purple segments, you create 4 congruent right triangles. So this is a 30, 60, 90, which means this must be a 30, 60, 90. So obviously this angle is the smaller angle, that's 30, so obviously this angle must be 60. So omega must be 60 degrees. There's not a lot of math you have to show for that. Some of these problems don't really require a lot of math. But I gave you the room down here just in case you want to do any math that you need to do. So if you got those right, good job. Let's go on to number 10. Try number 10. When you come back, we'll do it together. All right, we're back. So these are exterior angles of the polygon, exterior angles, which means we're going to have to use the polygon exterior angles theorem. That tells us that the sum of the exterior angles is always equal to 360 degrees. So that was a pretty easy formula there to remember. So let's add up these angles. We have y, the red y, that's one angle. We have 91 and 92. You don't have to write the degree symbols yet. And 88, they must add up to 360. So you can use your calculator if you want. 91 plus 92 plus 88 is equal to 271. And then subtract 271 from both sides. And we get 89. So y is equal to 89 degrees. If you got that one right, excellent. Okay, so on to number 11. If the number below is the sum of the measures of the interior angles of a convex polygon, find the number of sides of the polygon. So we know that the sum of the interior angles is equal to 180 times the number of sides minus 2. We're told that the sum of the interior angles, which is S, that's equal to 1260. So we can just plug that in and just solve the equation. Now there's a lot of different ways to do this. You could actually go ahead and divide both sides by 180. That's actually the easiest way to do it, and just use your calculator. But a lot of students, they don't really want to do it that way. So instead of doing it that way, what you can do is use the distribution rule, or the distributive property. Multiply 180 by n and you get 180n, and multiply 180 by -2 and you get -360. That's just another way to do it. Then you want to add 360 to both sides. So 1260 plus 360 equals 1620. Then divide both sides by 180 and you get 9. So there's 9 sides of that polygon. So if you got that answer, good job. Okay, now if I really wanted to be stingy about this, I would make you write a final answer and say 9 sides, but I don't really care, to be honest with you, if you do that. If you just rectangle this, that's good enough for me. Okay, is the following triangle an acute, obtuse, or right triangle? Go ahead and try number 12, and when you come back, we'll do it together. All right, we're back. In this problem, we're going to have to use the Pythagorean inequalities theorem, which tells us if the square of the longest side of a triangle is greater than the sum of the squares of the other sides, then that triangle is obtuse, meaning one of the angles in the triangle is greater than 90 degrees. If the square of the longest side is less than the sum of the squares of the other sides, that means the triangle is acute, meaning that there are no angles in the triangle that are greater than 90 degrees. So we're going to write a Pythagorean statement here. We're just going to put a bubble because we don't know if these expressions are going to be equal or greater than or less than, or so on and so forth. Also, I forgot to mention, if they're equal, then that means it's a right triangle. That's the Pythagorean theorem, the converse of the Pythagorean theorem. So the longest side is obviously 3 root 3, so I want to plug that in here. You can see just by looking at the triangle, it looks pretty long compared to the other sides. And it doesn't really matter which side goes where on the shorter sides, A or B. And all we have to do is simplify. And 3 root 3, that's 3 root 3 times 3 root 3. 3 root 3 squared, that is. 2 squared is 4. And over here we have the square root of a number squared. So squaring is the opposite of square rooting. So they just cancel each other out. So you're left with 23. 3 times 3 is 9. And if you're a little rusty on how to multiply roots, you can go back to my beginning algebra course. And I should probably color these so you know what's happening here. Root 3 times root 3 is just root 3 times 3. So I'm showing you where these numbers are coming from. So then we get 9 times root 9. You don't really have to show all this work, and I don't really have the room to show it, but root 9 is 3, and 3 times 9 is 27. When you multiply a root by itself, it's again, just like up here, it's the opposite of square rooting. So you just get rid of the root. Again, you can review all that in my beginning algebra course. So 4 plus 23, that's 27. And you can see here, they're actually equal. So now we can get rid of our bubbles. Well, we probably should just keep the bubbles. And we write equals inside the bubble. And what that proves is that this is actually a right triangle. It's not obtuse and it's not obtuse. It's a right triangle. So we can just use the adjective right down there. So if you got that one, good job. Let's draw a divider and go ahead and try number 13. When you come back, we'll do it together. All right, we're back. So this is a parallelogram. We learned all kinds of theorems. We learned the parallelogram opposite sides theorem, the parallelogram opposite angles theorem, the parallelogram consecutive angles theorem, the parallelogram diagonals theorem, and so on and so forth. Hopefully I remembered those names correctly. So B is the opposite side of the side at the right there, which is 4. So B must be equal to 4. Very easy. And X is the opposite side of this side 7 here. So X is obviously 7. Very easy. Theta is the opposite angle, so we learned the parallelogram opposite angles theorem, which tells us that those angles must be congruent. So theta is 116 degrees. And by the way, that was the parallelogram opposite sides theorem that told us that these are equal length. Now to find y, we're going to use the parallelogram consecutive angles theorem, which tells us that consecutive angles, angles next to each other, are supplementary. So we know that y plus 116 must be equal to 180. And if we subtract 116 from both sides, we get 64 degrees. So y is equal to 64 degrees. If you got that one right, good job. So let's go on to number 14. A woman looks down at a seashell on the beach. The angle of depression is 41 degrees, and she is standing 8 feet from the shell. How tall is she? So, angle of depression means she's looking straight forward, right? She's looking straight forward, and then angle of depression is the angle that she looks down to see the seashell. So that's 41 degrees. So there's a couple different ways we could do this, but we need to take this triangle out and be absolutely sure what's going on here. So if you want, we can deal with this triangle here, or we can deal with this triangle. It doesn't matter. They're both the same triangle. I'm going to use the top one because that's where our angle's at. So that's 41 degrees, and it's very important to understand that this distance here on the triangle, that's the same as this blue distance, which is 8 feet. So we can make this side 8 feet, and we're looking for how tall she is, which is the same as that blue distance over there. So that's this blue distance here on the triangle. So we'll put a question mark for that, or actually instead of a question mark, we'll put a variable. We need to use some sort of a variable, so let's just use, actually let's use h for height. Okay, so now we have a side of a right triangle. Of course, this is a right triangle because we're assuming that the ground is flat and she's standing straight up. So we need to find a relation between the side and the angle of the triangle. That's trigonometry. So this is our angle that we're given, and we have the adjacent side and we have the opposites, or we're looking for the opposite side. So adjacent and opposite, that's tangent. So we write tangent 41 degrees is equal to the opposite side of that angle, which is h, over the adjacent side, which is 8. So now we just have to solve that, and we're trying to isolate h, get it by itself. It's not by itself because the 8 is next to it. So we have to multiply both sides by 8. So times 8 on both sides. And then we end up with 8 times tangent 41 degrees is equal to h. And that's going to be our answer. We just have to do a little bit of calculation. So let me find some more room here. So we cannot do this without a calculator. We could use advanced mathematics, but we haven't learned that math yet, so we have to use a calculator. So if you're using an iPhone, there's a lot of different ways to do this, but one way is enter 8 and then the times button, multiplication button, and then 41, and then the tangent button, and then equals. And does it say to round off? It says, well, it doesn't say what to round off to, so that means we can just round off ourselves. So I'm going to round off to the nearest 100th place. This woman is pretty tall. She's 6.95 feet. 6.95 feet tall. So she's probably a basketball player or something. Now you could say 7. You could round it off to 7 feet, or you could round it off to, well, that's about it. You could say 6.954 feet. It doesn't really matter because the problem doesn't tell us what to round off to. All right, so if you got that one right, good job. Try number 15. When you come back, we'll do it together. All right, we're back. It says find the unknowns in the kite below. So we know that this is a kite. Now, we learned a lot of theorems for kites. One theorem is called the kite congruent angles theorem. That tells us that these angles in between non-congruent sides are congruent. So if this side is 118, then omega must be 118 also. So that's pretty easy. A lot of the problems on this test are just memorization. If you remember the theorems, then you can answer them pretty quickly. If not, it's going to be very difficult. Now, a kite is a quadrilateral with two pairs of congruent sides. So this side and this side, they're congruent. And this side and this side, they're congruent. So we know that the pink one expressions, they must be equal to each other. So then we just solve that, subtract 2c from both sides, subtract 1 from both sides, and there you go. C is equal to 3. Maybe I'll just write that there and put my work down here. You can do it either way. You don't have to write your answer up here. You can write it down here if you want. That's fine. As long as you rectangle it so I know where it is. In fact, you should only rectangle it in one place, though, so I don't get confused about where exactly your answer is. You don't want multiple answers. If you got that one right, excellent, good job. So, on to number 15. It says find the unknowns in each trapezoid below. So go ahead and try number 16. When you come back, we'll do it together. All right, we're back. So these sides here are bases of the trapezoid. Now I know that this upper side here doesn't seem like a base because it's not at the bottom. Usually base means at the bottom, right? The foundation of the structure. But you can flip this trapezoid upside down and this would still be considered a base. So these parallel sides are the bases. These sides are called the legs. They're not usually they're not parallel. If they are parallel, then you would call the quadrilateral a parallelogram instead of a trapezoid. Now, we learned something called the trapezoid non-base pair theorem, which tells us that if you have angles that are not a base pair of angles, then those angles are supplementary. Now, what that means, base angles are angles here and here, and angles here and here. So they are angles that have a common side that's a base. That common side for these two would be this base, and the common side for these base angles up here would obviously be this base. But non-base pair angles are angles where these two here, where the common side, which is this side, the common side of those angles, that's not a base. So they're non-base pair angles. This would be another pair of angles which are non-base pair, because the common side of those angles is this side, which is, again, not a base of the trapezoid. So those are supplementary. So to find x, we just add x and 124, and we should get 180, which means if we subtract 124 from both sides, we get 56 degrees for x. There you go. It's that easy. Now you can write your answer down there, or you can write your answer up here. It doesn't really matter. But you do need to show some work. Now the same is true for those other non-base pair, the non-base pair at the left. So omega plus 52 must be equal to 180. Subtract 52 from both sides, and we get 128 degrees. So there you go. I'm going to write the answer up there, because that's the way I started to do it before. So if you got those answers, good job. Let's try number 17. These are also trapezoids. The problem tells us that these are all trapezoids. So try 17. When you come back, we'll do it together. All right, we're back. This is an isosceles trapezoid. Now, how do I know that? Well, because it tells us these sides are congruent, because they have that red mark there. So this is an isosceles trapezoid. That's the definition of an isosceles trapezoid, when the legs are congruent. But we learned the trapezoid diagonals theorem, which tells us that if a trapezoid is an isosceles trapezoid, then the diagonals are congruent. So if DF is equal to 10, that means that EG must also be equal to 10. So that's a pretty easy problem. It doesn't get much easier than that. Of course, that is if you remember the theorems. It's not easy remembering all those theorems, is it? So if you got that one right, good job. Try 18. When you come back, we'll do it together. All right, we're back. So this theorem is the trapezoid one pair base angles theorem. That tells us that if one pair of base angles are congruent, then it must be an isosceles trapezoid. Now remember, the definition of an isosceles trapezoid is the legs must be congruent. So that means that y plus 1 must be equal to 3, which means y is equal to 2. So there you go. So if you got that one right, good job. Y is part of this expression, so I'm not really requiring you to write a unit there, even though a lot of teachers would. I don't really care one way or the other. Okay, so go ahead and try number 19. Find the unknowns in the rectangle below. When you come back, we'll do it together. All right, we're back. This is a rectangle. And a rectangle is a quadrilateral with 4 right angles, but that doesn't really help us in this problem. But we did learn something called the rectangle parallelogram theorem. which tells us that if a quadrilateral is a rectangle, then it's a parallelogram. So all the theorems that we learned relating to parallelograms, they also work for rectangles. So remember, opposite sides of a parallelogram are congruent. So B must be 7 centimeters. Also, remember the diagonals of a parallelogram bisect each other. So this is a rectangle, which means it's a parallelogram. So they bisect each other. But that actually doesn't help us because we don't know the other side there. We have a theorem that tells us that the diagonals of a rectangle are congruent. So if these lengths, these orange lengths, are both equal and they both bisect each other, then that means all of these lengths, the yellow one and the purple one and the blue one and the green one, they all must be the same length. So that means y obviously must be 4. Y is 4 centimeters. Actually, I think I'll just get rid of the centimeters there because I don't really have a lot of room. All right, let's go on to the next problem. Find the unknowns in the square below. So attempt number 20. When you come back, we'll do it together. All right, we're back. We need to use the square two special triangles theorem that tells us if you draw the diagonal, one diagonal, you can draw two diagonals, but if you draw just one diagonal, that diagonal creates two congruent right triangles, the yellow one and the blue one. They're both right triangles. So that means that W obviously must be 90 degrees. The theorem actually tells us that the triangles are special triangles, that they're 45, 45, 90 triangles. So theta must be 45 degrees. And alpha must be 45 degrees also. And in order to find C, we have to refer to our 45, 45, 90 degree triangle theorem, which says that if this angle is 45 and this angle is 45 and this angle is 90, then whatever these angles are, the hypotenuse must be that number times root 2. So we're told that this side here is 15, so that means W is 15. So that means C must be W root 2. C must be W root 2. So W is 15, so W root 2, and that is inches. If you got those right, good job. On to number 21. So now we're moving on to the proofs. This is the most difficult part of the test. We have 5 proofs, and then we'll be done. So it says, show that the following statements are true using 2-column proofs. You might not use the same number of steps written in Roman numerals. You may use more or less, so be aware of that. I have 3 steps here, but maybe you'll choose to use more or less than that. You can write more steps if you need to. But this particular problem, you're only going to need 3 steps. So it says, if the quadrilateral below is a square, then it is a rectangle. So if it's a square, then it must be a rectangle. We have to prove that. So what's the given information? Well, go ahead and try number 21. Remember, I know that proofs are very intimidating, but don't complain unless you write the until you write the given information. So write that given information and attempt this proof, and when you come back, we'll do it together. All right, we're back. So we can say A, B, C, D is a square. That is given information. They told us that. We know that that's true because they told us. Now, we need to somehow show that that means that it's got to be a rectangle. Well, what's the definition of a rectangle? A rectangle is a quadrilateral with 4 right angles. Now, if ABCD is a square, remember the definition of a square is a quadrilateral with 4 right angles and all sides are congruent. So the idea that a square has 4 right angles, that's just part of the definition of a square. So we can say that angle A, angle B, angle C, and angle D are right angles. And that's just the definition of a square. Okay. Now, at that point, because all 4 angles are right angles, we can then say that ABCD is a rectangle. Because that's the definition of a rectangle. It's a quadrilateral where all 4 sides are, all 4 angles are right angles. So that's just the definition of a rectangle. So that was pretty easy. So again, ABCD is a square, that's given, which means all the angles must be right angles by definition, but that's also part of the definition of a rectangle, so it must be a rectangle. So if you got that one right, good job. On to number 22. Go ahead and attempt number 22. When you come back, we'll do it together. All right, we're back. If the figure below is a kite, then angle D is congruent to angle B. So I want to mention that this is the kite congruent angles theorem. You can't use the kite congruent angles theorem because that would be too easy. You just write one step. Or actually you'd write 2 steps. So we're not going to use that theorem. We're just going to prove the theorem. So the given information is that ABCD is a kite and what we're going to do is we're going to prove that this triangle is congruent to this triangle and then use CP/CTC, corresponding parts of congruent triangles are congruent, to show that these angles are congruent. So it's a pretty simple proof. So we need to show that those 2 triangles are congruent though, and maybe I should keep those colors there so you can see exactly what we're trying to do here. Again, we're trying to show that the yellow triangle is congruent to the blue triangle. So we know that DA is congruent to AB. How do we know that? Well, that's just the definition of a kite. A kite is a quadrilateral with 2 pairs of congruent sides. We also know that DC, the other pair, they're congruent. So DC must be congruent to BC. And that is the definition of a kite also. You could combine these into one step, and maybe we should do that depending on how much room we have. Or maybe I can just add another step if I need to. We also know that AC is congruent to itself by the reflexive property of congruence. Reflexive property of congruence. And we can then say that the triangles are congruent, and I guess I should have combined these to one step. I'm just going to demonstrate that you can actually combine those to one step if you want to save writing that twice. That's one way you can do it. That's what I mean when I say that you can use more or less steps. Just because your proof isn't exactly the same as mine doesn't mean that it's necessarily wrong. So then we say that triangle ADC, and if you're going to write a triangle congruent statement, make sure that it's a proper statement. We started with A at the top, so we have to start with A in the next statement, and then go to the right and then down. So now the letters are lined up properly with corresponding vertices. And that is the SSS, side-side-side triangle congruence theorem. Actually, postulate, it's a postulate. Now we know that the yellow triangle and the blue triangles are congruent, which means that corresponding parts of congruent triangles are congruent. All the corresponding parts are congruent, so that means that obviously angle D must be congruent to angle B, and that's what we're trying to prove. So there you go, we did it. So if you got that one right, good job. On to number 23. We've got 3 more problems. It says, if the figure below is a trapezoid, then angle A and angle B are supplementary. It says you must use a transversal theorem. So go and attempt this one, and when you come back, we'll do it together. So we know that this is a trapezoid, and we're trying to prove that this angle and this angle, those two are supplementary, meaning they add up to 180 degrees. So the given information is that ABCD is a trapezoid. That's given information. Maybe I should move that line over. And a trapezoid is defined as a quadrilateral with one pair of parallel sides. So we know that AD is parallel with BC. That is just the definition of a trapezoid. I'm just going to draw a picture of a trapezoid. It's kind of a long word. And so, very important to understand what we've done. We've shown that this line here is parallel to this line. So what that means is that if you have a transversal going through them, you can use all of your transversal theorems. We have corresponding angles are congruent, corresponding angles postulate, that is. We have the alternate interior angles theorem. We have the alternate exterior angles theorem, and the one that we're going to use is the consecutive interior angles theorem. If those orange lines are parallel, then consecutive interior angles are supplementary. So angle, let me get rid of these, angle A and angle B, these angles over here, they must be supplementary by the consecutive interior angles theorem. So angle A and angle B are supplementary. Sorry about that, it's kind of scrunched in there. And that is the consecutive interior angles theorem. So if you got that one right, good job. Again, if you're having trouble with these, that's okay. That's why we're doing this practice test, to get you warmed up so you have an idea of how much you really need to study in order to prepare for this test. Again, math exams must they require at least 2 days of studying before you take the exam, or else you're just going to waste your time and waste my time failing the exam. Because if you fail the exam, that means all the effort that I put into it was for nothing. All right, number 24. If the quadrilateral EFGH below is a rectangle, then it is a parallelogram. So go ahead and try this problem, and when you come back, we'll do it together. All right, we're back. So we're going to show that this rectangle is a parallelogram. And remember, a parallelogram is a quadrilateral with 2 pairs of parallel sides. So we have to show that this side is parallel to this side, and this side is parallel to this side. That's going to prove that it's a parallelogram. And the way that we're going to do that is we're going to consider that all the angles in a rectangle are right angles by definition. Now, we don't need 4 angles. We can just use 3. So just pick any 3 angles. And we're going to start with 2 angles and say, because these are both right angles, that means the measures are 90 degrees. And if you add them up, you get 180 degrees. And by definition, that means that they're supplementary angles. But if you have 2 lines cut by a transversal and the consecutive interior angles are supplementary, that proves that the purple lines are parallel. So that's how we're going to do this. They're interior because they're in the middle of the purple lines, and they're consecutive because they're on the right, both are on the right of the green line. Now we're going to do the same thing with 2 other angles. We can use these 2 down here, or we can choose the 2 up here. It doesn't really matter. We're going to do the exact same thing, and that's going to prove that these 2 sides, which are cut by this transversal, those 2 sides are parallel because, again, the orange angle measures, they add up to 90, which means they're supplementary. If they're supplementary, then the green lines must be parallel. So the given information is that EFGH is a rectangle. We know that. That's given. Angle E, angle F, and angle G are right angles. And that is just the definition of a rectangle. Now, that also means that the measure of angle E is equal to 90 degrees. The measure of angle G is equal to 90 degrees. And the measure of angle, actually, whoops, I forgot F there. The measure of angle F is 90, and the measure of angle G is 90 degrees. That's just the definition of a right triangle. Oh, excuse me, right angle. Sorry about that. Right angle. Okay, so now the measure of angle E plus the measure of angle F must be equal to 90 plus 90. So all I did was I just substituted in the 90s for E and F, the measures. But it's also true that the measure of angle F plus the measure of angle G, you can do this separate in a separate step, and I'm just going to put it into one step. Using substitution, we can plug in those 90s. So then we know that the measure of angle E plus the measure of angle F is equal to 180 degrees by simplification. And the same is true for the measure of angle F plus the measure of angle G. Those add up to 180. But what that means is that angle E, and again, notice that I combined these all to one step and I combined these to one step. You don't have to do that. You can break them up into multiple steps. It's just going to mean you're going to have to write more than one step, and you're going to have to write substitution twice and simplification twice. So if the measures of the angles add up to 180, that means angle E and angle F are supplementary. That's just the definition of supplementary angles. And angle F and angle G are supplementary. So definition of supplementary angles. So we're pretty close to finishing our proof here. If angle E and angle F are supplementary, that proves by the consecutive interior angles converse theorem that these two segments must be parallel. That's what we're trying to prove, because we're trying to show that it's a parallelogram. Parallelogram means two pairs of parallel sides. So we can now say that EH is parallel to FG, segment EH and segment FG. And we can also say, because F and G are supplementary, that proves that these segments are parallel. So EF is parallel to HG. And that's the consecutive interior angles converse theorem. So we proved that there's two pairs of parallel sides in this quadrilateral, which means obviously that EFGH is a parallelogram. And that's just the definition of a parallelogram. And I'm going to draw a picture of a parallelogram because I don't have much room there. Alright, so that proof was a little bit more difficult. So we have one more proof. If you got that one right, that's very good. If you got stuck, that's perfectly fine. Most students will get stuck in proofs. That's just completely natural. Don't feel any distress. You just need to get some more practice and you'll do fine with some practice. So number 25, if the quadrilateral below is a parallelogram, so we know this is a parallelogram. If it is a parallelogram, then AB is congruent to DC and AD is congruent to BC. So that's what we're trying to show, that the yellow ones are congruent and the blue ones are congruent. So this is the parallelogram opposite sides theorem. But we're proving that theorem. You can't use the theorem to prove itself. So we know that ABCD is a parallelogram. And by the way, go ahead and try this problem if I didn't already tell you. I gave you the given information. Go ahead and attempt the problem. When you come back, we'll do it together. But you need to try this one on your own first. All right, we're back. So that's the given information. The way that we're going to prove this statement is we're going to draw an auxiliary line, and we can draw one here or we can draw one here. It doesn't really matter. You can prove it either way. So I'm going to draw this auxiliary line, and I'm going to make it a dotted line because it's or a dotted segment because it's not really part of the parallelogram. We're then going to show that this triangle here is congruent to this triangle. And once we show that those two triangles are congruent, then we can say that corresponding parts are congruent. So this side is congruent to this side, and this side is congruent to this side. That's what we're trying to show. So in order to do that, we have to use the definition of a parallelogram. A parallelogram is a quadrilateral with two pairs of parallel sides. So we know that AB, for example, is parallel to DC by the definition of a parallelogram. And I'm just going to draw a picture because it's kind of a big word to fit in there. Now, we're also going to use the fact that AD is parallel to BC. We need that also to show or to prove this statement up here. So we could combine that into one step, and And I'd welcome you to do that, because that means you only have to write this reason once rather than twice. But to make things a little easier to understand, I'm going to use more steps here. So based on the fact that AB and DC are parallel, we're going to show that some of these angles are congruent. So I'm going to draw a line through AB. So I'm going to extend out that side of the parallelogram, and I'm going to draw a line through DC, extend that out, and then I'm going to extend out this auxiliary segment there, and I want you to ignore these sides of the parallelogram. I know that's kind of hard to do, but just focus on the green and the orange. When you focus on the green and the orange, you can see that this angle here is congruent to this angle here based on the alternate interior angles theorem. The green lines are parallel, so alternate interior angles created by a transversal, they must be congruent. So remember, we have the corresponding angles postulate, the alternate interior angles theorem, the alternate exterior angles theorem, and the consecutive interior angles theorem. We have all four of those. We're only going to use one. So we know that angle ABD is congruent to angle BDC by the alternate interior angles theorem. So now we can erase all that stuff. And you see those purple arcs are angles in the triangles. Now we're going to use these sides here. I'm going to extend that out just so we can see what's going on here. I'm extending out those sides, and we're going to again draw the auxiliary line. It's kind of hard because we're going over the letters, but you can see that again we have two parallel lines, the green, cut by a pink transversal, and we can say that this orange angle here is congruent to this orange angle down here, because those are also alternate interior angles. Now again, ignore these sides over here on the parallelogram. So we can now say, based on the fact that AD is parallel to BC by, again, the definition of a parallelogram, we can say that angle ADB is congruent to angle CBD. And that's, again, the alternate interior angles theorem. Now, just to be sure that we notated those angles properly, let's erase all this, because that kind of went over the letters. So ADB, the orange, is congruent to CBD, the other orange at the bottom left. So that looks correct. And up here, let's just make sure this is right. ABD, the purple at the left, is congruent to BDC, the purple at the right. So that all looks correct. You want to double check because it's easy to get confused here. So we showed that the purple angles, and I should probably use a double arc for some of these. I'm going to use a double arc for the purple. So we showed that the double arc purple angles are congruent and the single arc orange angles are congruent. But we also know that BD is congruent to itself. The auxiliary segment, BD, is congruent to itself. And the reason that we did all this is to show that the yellow triangle and the blue triangles are congruent. And by the way, that is the reflexive property of congruence. So what that means is, because we have two triangles that have two pairs of congruent angles and the side in between those angles is also congruent, we can say that the two triangles, the yellow triangle and the blue triangle, are congruent by the ASA triangle congruence postulate. So triangle, remember there's many different ways to write a triangle congruence statement, but once you decide the order of letters on one of the triangles, you have to keep the same order in the corresponding, or the other congruent triangle. So we started at A, so we have to start at C in the other triangle. We went from A to the purple double arc. So we have to go C to the purple double arc, which would be C to D, and then B. So now that we know that the triangles are congruent, now we can say that corresponding parts are congruent. So we can say segment AB is congruent to segment DC. Because corresponding parts of congruent triangles are congruent. And it looks like I have another step there, but you really don't need another step. You can say in the same line that AD is congruent to BC, and that's what we're trying to prove. That's the last step. And whoops, I forgot to draw the segment above the BC there. So we did it. We proved that opposite sides of this parallelogram are congruent. And we don't really need the last step. You can combine these two purple steps into one, or you can combine the two green steps into one. That's fine. And you would need even fewer steps. So you don't need to use all the steps provided necessarily. It's just kind of a guide or a basic idea of how many steps you may need. So if you got that one right, good job. So now we're going to take screenshots of the work that we did to help you with homework or to study for tests. Remember, I'm going to give you a practice test for homework. And this practice test is going to help you do that. These tests are not optional. You must take these practice tests before going on to the next class. But don't go before you get your practice test. Let's get a screenshot of the practice test for homework. Here's screenshot number 1. And screenshot number 2. And number 3. And number 4. And number 5. And number 6. But don't go before you get the answers. Remember, it's not enough just to try the test. You have to get the answers right. So here's a screenshot number 1 of the answers. And screenshot number 2 of the answers. So get that practice test done completely, correctly, and neatly, and keep it in order in your binder. And I'll look forward to seeing you in the next class.